Thank you. It's exciting to be here. It's exciting to see a lot of interest growing in Yerevan for data science, machine learning, and things like that. I'm happy. Oh, maybe I need to turn on. How about now? Oh, very good. Yes. I'm happy that organizers managed to organize this real-time event. It was actually the first time I speak in front of the real public since February 2020, before the lockdown. So not far away. I went to Sochi to give a lecture just before the travel stuff. So it's great to have the real way interaction, because I think that's what our field was missing quite the most. So I am happy that the organizers didn't only prepare a great program, but took very great part and take care of us, like Arsen, Zab, and Ando, and Ran, that spent all day hiking with us 2 days ago in Tbilisi. So thank you very much. I also thank Vahan for organizing our trip, and Tatevik. Due to her, I know that organizer knew about me because of her. So thank you very much. So today we will talk about self-supervised learning. And why we care about self-supervised learning in DeepMind or in general in research doing using AI. The reason is that current world doesn't equip us with a lot of labels, right? A lot of machine learning, a lot of data science work with okay, we'll label all the data, and you can come up with a classifier or object detector or things like that. But for real, autonomous AGI, we need agents to generate significantly beyond the task that we're trained on. And this is not easy if we don't have a lot of labels. So we kind of need to create it. However, what the reality tells us that the supervised learning with a lot of labels, this is what actually machine learning and deep networks are good on, right? So the stuff that machine learning and deep networks are good on is not actually the stuff that we would like to achieve, for AGI in particular. So, and somehow the self-supervised learning is the way to get to that without too many labels. So, the claim at the end is that mastering self-supervised learning can equip our self-supervised agents with stronger generalization capabilities to going outside of the data they've seen and outside the labels and supervised information they've seen. So this is what is planned for today. I'll spend a little bit of time talking about what is the modern self-supervised learning, how our method works. We use particularly ResNet and encoder, but this is just one of the example how we apply our methods. I would like to focus more on the principle that we can employ, this Bootstrap Latent, and we use image and the data. That's why we're running example. But then, since we published our paper last December, we keep working on it and applying to other domains. So I mentioned work on that, in particular for graphs, for neural data, and for videos. And finally, in the last time, I'll try to build some intuitions, because we don't fully understand the mechanism, but we have some intuitions why they work. We tried a lot of other things, a lot of other people tried, explain why things work, and I try to explain what we think is behind it. Please interrupt me anytime with the questions. I don't need to go through all my slides. I have too many. I'm happy to adapt to what the audience would like to hear. So if there is any question now, I'm happy to hear it. And if not, there is some question time at the end. Okay, any questions for now? If not, we can start. All right, so what is self-supervised learning? So in computer science, the vision goal is to produce an image, to process the image to solve some kind of downstream task. And one downstream task could be classifications, segmentations, or object detection. Right, so this is a modern deep learning where the model is some kind of neural network these days, and the tasks are some example of tasks that practitioners may be interested in. This is vision application, right? But both of these are usually encapsulated by particular neural networks, so encoders. And here, for us, the running example, at least the first part of the talk will be just a simple ResNet, and the downstream task could be one very simple multi-layer perceptrons. So the hope is that the encoder, without any information, will extract some kind of visual representation. Before we used to call them features, just some features, so you can call it as feature learning, feature extraction. And then this feature extraction will be generic enough that they will be able to, the same features will be able to be applied for all these tasks to task at hand. But how? Then the question is how to actually train this neural network. So in reality, we have two kinds of data. One that's labeled, and we usually have to pay for the pay or spend time on labeling them. For example, taking the image and assigning label to them, or more specific, taking an image, taking the squares and labeling, particular subset of object. So this is, we have data sets like that, but they're costly. But if we come in reality with real world data, we usually don't have that, right? So the less time we need to spend labeling, the better, right? On the other side, the decades of machine learning is somehow trying to make use of this unlabeled data and learn something without human spending a lot of time to label them, right? And so in this talk, we talk about our method, which is a method to train the weights of this encoder network. So this is what we do. We train a generic encoder by using unlabeled data with self-supervised learning. And to train the network with labeled data later, just this little network, that hopefully will take very little time, for particular tasks. Now we will have particular label because we need to actually tell the network what is the task is. But the hope is that there will be massively less labels needed because most of the work has been done here already in encoding the features. So that's where we are. All right. So this is the setup. If somebody has a question now, this is also a good time to ask a question. Otherwise, I present this. You had a question? No, so now I'll present our method to train this ResNet, and which is a self-supervised method for pre-training image representation. So the many self-supervised methods for a long time are based on this principle. This is taken from the paper that predates our paper called Simple and Contrastive Learning. But the principle that starts all this is the same, right? So the main ingredient is to take some kind of advantage of image transformations. So, for example, if you take an image of a dog and transform it with random prods, reshape, color distortion, some core information such as breadth, shape, or posture is going to be preserved. So this is kind of main underlying principle that we don't need to tell the image that it's a dog, but we know that under this transformation it still stays a dog. So there's few important things to mention. I'm talking about the dog, but no network knows that's a dog. And at the same time, as I'm doing transformation of the dog, I'm doing also transformation in the grass. So I'm not only learning transformation for something specific, but for any possible thing that is in the image. And the hope is that under this transformation, this information will be preserved. So more generally, we can just expect this high-level semantic information to be preserved by this simple transformation. Another point to make that while we call it self-supervised learning as part of unsupervised learning, it's not completely true because here it's exactly where the human needs to put knowledge into that, right? So I was a human that decided that, okay, it's actually crop and resize and color distortions are the good transformation that if my network will be invariant, so if I do this transformation and pass it to the network, the output would be almost the same. So this set of transformation had to be designed by a human. And now I'm just presenting like this on the slide, but there is decades of computer visions that try a lot of this transformation. It's kind of understood what is transformation now. Now, if you have some new example, sound, vision, tabular data, it's very difficult to come up with this transformation. Some of them are easy. Usually crop is the basic one, but more fancy one or more ones that are data specific, it's very difficult. So while we call these things self-supervised, it's not completely, unsupervised, or it's not completely AGI, because this is the part that somebody had to say, I want the network to be invariant to this transformation. So that's a point that I would like to make here. All right. So, and the BIOL and many other methods work on this main intuition that given a transformation of the image, if we look directly to predict another transform mu of the very same image, because we know this transformation are done on the same image, so we know that what we're predicting should be the same. So again, the bulk views contain the same semantic information, and we should be able to predict their representation independently of this transformation. All right, and so this is how BIOLs approach it. So we process the first view with the encoder. This is something that we do train, and on top of that, and this is something more specific to our method, we add this additional predictor, which is simpler multi-layer perceptron, and it predicts whatever the recurrent weights are able to predict. So, however, now remember that we're dealing with unlabeled data, so we don't have any. Originally, we don't have any gradient descent that's coming from the loss. That is coming from the labels, because we just simply don't have labels, so we cannot train it out of nothing because we don't know these labels. And this is where the second part comes in. And so we need to find a way, and now I describe it, how to generate our own targets. So we process a second view to compute these targets. And before I need to continue, I need to point out a few things, right? First, we only train the top network making the prediction, but we do not propagate the error through the targets. This is super important because we don't want to encourage the views to be predictive of each other. This is something that would cause the phenomenon that's called collapse very easily. Collapse means that network is trained that everything outputs the same number, same vector of numbers, zeros or something else, and such embedding is useless for downstream tasks because features that are same for every image, they're not very useful. So that's the first thing. Second, for BIOL, both the prediction and the target outputs are continuous vectors. But this is also a difference from some work in the past, where you try to somehow cluster and assign some kind of fake label, if, for example, in Moco deep cluster, as a target. Here we are working in continuous space, so this is actually good for us because we can use simple L2 loss, so simple L Euclidean loss, because we work on the embedding level. So this is L2 loss, or if you normalize predictions, which is also something that we do and it makes sense, it's also called cosine similarity. So, yes, please.
I think that when I was raising your hand, maybe you already answered my question. My question was, why do you need predictor? Why you can just take output of encoder 1 and encoder 2 and use cosine distance? And
well, we predict by the output of the other encoder by using the cosine distance.
So you take one vector from the first encoder
and one vector, and then you do the L close. So this is a vector. This is a 256 number, another 256 number. We do the difference, square it, and the gradient of that is put through the first part, but not for the first part.
So what is predictor then?
What is not the predictor, where the loss that is sent is the loss. Are you different from the target predictions? And if you're different from the target predictions, the gradient to reduce the difference from the target predictions is used to update the weights. So you're predicting, for a beginning, I'll talk about it, random labels,
But in your case, you say that you are not predicting labels. You are predicting
you're predicting some card, you predict continuous vectors. Exactly. So it's not a classification, it's more of a regression.
So I can get why you have predictor on top and not So either you should have predictor on top and on the bottom. Why do you need predictor only on top?
So the whole process, we actually don't care about what the predictor. Whole process is that come up with some strong encoder. After end of the process that I haven't described yet, we throw out everything else and we just output the encoder. And that's our output. We don't care that that it's predicting something and to train them.
I can understand.
And the way to train this encoder, we use some kind of gradient descent to train the weights. But to train the weights, we need to somehow come up with some kind of supervised signal. And the supervised signal that we decide to create, maybe some other thing could work as well. I'm not saying this is the only way. We decided that the simple thing would be just take the L2 loss, because it's the simplest thing, differentiable, to predict. But it's very likely that some other loss would work as well.
Okay, so during self-supervised training, you don't use predictor.
During the self-supervised training, we're training everything. We're training everything on the top level, and I will describe in 2 minutes what we do on the second level.
Okay.
But if I didn't answer your question, please come back to me in 3 minutes. After maybe it will be a little clearer what we actually do, because here it's very high level. Okay, and so then once we have this that I almost described, once we have these target predict labels, or you can just get it embeddings or target prediction, we just do we just ask the predictor, the output of this network, to predict the targets, right? So we regress. We want this, the output of this, to be as close as possible what comes from this. So we take an image, process it both ways, see what comes out here, see what comes out there. Well, it will be different, and we want to minimize the difference, but only updating the weights on the top. So this is the very high level, but now I will go slightly more into details. All right. So if we do so, if we first try to predict these random labels, an interesting phenomenon is going to happen. Right? So again, imagine our labels are very random, right? So they are random weights, and so predicting label is something random, something that doesn't make much sense. But if we train the top network to predict this random label, we already do better than random predictions. So there is a difference between random prediction. This is just you pick a label from the uniformly at random, but predicting network with random weight, it's not the random prediction. It's something that's coming from the random weight. And we already, if we just try to predict these random labels, and we do this, we train this, we already get some reasonable embeddings. And on the evaluation that I will describe later, we already did something like 18% by predicting something that's close to noise, but it's processed by the network. So even if we keep the target network fixed and random initialize and randomly initialize the weights, the process allows the encoder to learn the better visualization than the random initialization. Then if we just do the random weights and see what's going on. So from there, the natural idea is to replace the random network generating targets with this newly trained encoder. And as a result, we can generate higher quality labels, right? So what we do, we train this encoder. We said, well, okay, it's not perfect, but it's better than nothing. It's better than random weights. And what we do, we replace them and we say, well, instead of giving us these random labels, labels coming from the network with random weights, we'll just use this slightly better encoder. And we get slightly better targets. And as you can see what is coming, we'll iterate this procedure. And by predicting these new, better targets. And then if we keep bootstrapping the encoder representation into the targets, we keep improving the encoder. And we do so until the convergence. And once we are not keeping improving, we can stop. All right, so this is the high-level idea, and the next slide I'll be slightly more detailed, but if there is a question about high-level idea. Yes?
Small question. Can you please verify what's the difference between the upper row and bottom row?
Okay.
You have the initial dog, then you make the crop of the dog, yeah?
Yes, yes. So I randomly select some kind of transformation. Actually, maybe I will be answering you with the second slide, because that is slightly detailed what is going on. So we take the dog, we pick a random transformation. More specifically, we do a set of transformation. We have around 12 transformation. Each we apply with certain probability. So maybe the dog is cropped and transformed, and this is also very much tuned, and it's all important to get it right. And another set of transformation that we create another version of them. But you can think of it, these are two random versions of the same image, right? Then we put into the ResNet that has an output, and this is the output that, for example, that has 2056 numbers. So the output of this ResNet is 256, for example, or 2056. Let's say 2000. And this is what we can output. And then, since it's much easier to find the predictor for small number, we can actually project these 2000 numbers to smaller, to 256. We reduce it 10 times. And now you could say, well, we can output the final features as this 256, but this would not be enough for downstream tasks. You cannot be. You need to have the numbers that are equally enough expressive, and 200 is not expressive enough. We tried, but projecting to the smaller space helps the task for this prediction much easier, because now now we are smaller dimensional space, and it will be easier to make this prediction, right? So there's two layers of multi-layer perceptrons. So after ResNet, and at the end, this is all the output that we take. We have this 2000. Now we have 256, another 2056 for prediction. That gives us the predictor, the predicted numbers. And what's going, so now answering the question, what's happening on the bottom is exactly the same thing, except we don't have this predictor. So we have one multi-layer perceptron less. And this asymmetry is very important. So this is specific what we do. Like the networks are exactly the same, the structure is exactly the same, but the weights will be different of this. So here it is not happening. So as we do step of the training, so we backpropagate the information, so we update all these weights. And for this, if we don't update it, it will not work very well. But what we do, we in high level we just replace thing with older version of what is on the top. So the bottom is somehow older version of this top. More practically, and what works better, instead of having just replacing it, we use empirical moving average of that thing. So you can imagine you have, for example, 100 of last steps, so 100 of last ResNets, and you do some kind of exponential moving average of those of the previous time, right? So let's say you pick up some coefficient that you tune, for example, 0.7 times weight from the last iteration plus 0.7 squared times weight from the previous iteration, and so on. So you kind of an exponential moving average, which is also easy to maintain in memory because you only need the one copy. What you can do, you always take my weight, multiply it with 0.7, and add it to the current weight. And that's your easily maintain the average. It's called also Polyak averaging, the typical scheme. Once you process those things, here you have embeddings, here you have the target, so the Z data is the output of projection, Q is the version of the prediction, and you would like these things to be close. So what you do Q theta Z, so the prediction, minus our target level squared. If you normalize it, so if you take Q0, Q theta Z theta minus Z prime C squared, and you normalize it, so like divide it by norm of this, divide it by norm of this, And if you redistribute and simplify, you get this expression, which is also a cosine similarity between two vectors. We can think of that, this is a vector in the space, this is another vector in the space. I want them to be same, but if they're different, the difference between that, the cosine similarity, is the signal that I put in the network. I pass the signal, all of that, I update the weights of predictor, projector, and the ResNet, and then I copy the old version or update the old version using the top version. It's clear?
Yeah, overall that's clear, thanks. Just a small clarification. The asymmetry which you talk about, and told it's very important. The asymmetry is only in missing this prediction part at the bottom, or
yeah.
there?
So in missing the bottom, and then the gradient doesn't propagate.
Yes, but it doesn't matter how many projection layers you have. It's just under asymmetry, you mean only the prediction part.
Yes, exactly that.
Thank you.
One layer, everything else is structurally exactly the same. Any other question? Okay. All right. So the key ingredient to keep here, we need image transformation. This is something that human needs to do. So one thing that we still don't know is how to get rid of this need for the transformation. The other thing to make it work is to have the target networks to generate the labels. This is also a difference. And there is additional predictor on top of online network. This is how much we are mostly, so quite a small structural changes with respect to the previous method. So why this is interesting, and why practitioners like this method, that it's pretty simple, I just will try in a few minutes. But the most thing that is most exciting is that, and I'll spend more time on it, that it doesn't require negative examples. So here we only try to make things that are, as Grigori said, similar to each other. We provided two embeddings of the same thing, and we said, well, if it's a good embedding in embedded space, so its features after encoder should be closer. And we didn't say anything about if we have different images, because we didn't need to somehow. I'll talk about it later. And the other thing is also very simple. It works on embedding level, and so usually in neural networks it works better if these things are continuous. So we directly can do L2 loss, and this is this behaves very nicely. So this is more like a practical interest of our method. All right. So back before Bio, the whole world was doing something completely else. The whole world was doing, and this is a slide from the people that did something else, was built on the contrastive learning. So it was built on something that's still very much present, that has both things, has trying to put similar things closer to each other and dissimilar things further from each other. And this is, if you look at the field, how it evolves. So this is the performance on of the ImageNet, and you see that from July 16 to now, and somewhere here right now, there were quite a big advances in the top 1% prediction, which is a main metric. And so up to Bio, that I'll show result later, the best methods were doing this constructive learning. There are actually even other methods, but in interest of time, I will not talk about it. Some methods there are, for example, generative methods, variational encoders. The most methods that were the method that had the best results up till now were the ones that creating two pairs, positive pairs, same as in Bio, and also the negative pairs. And so how. I don't know if I can have it on. So normally I would have the slide here, but it's a PDF. So it's almost the same as Bio, but the loss is different. Maybe I'll show it in the Bio being here. So the simpler version is that you have always the copy of the online network is exactly the same as in target network. So with the two Siamese structure. and you don't have the stop gradient. But you need to have your loss is much more complicated. It's not just comparing two things. You're comparing the two things. You're putting closer things together, but then you take every other thing from your data set, ideally every other thing from your data set, and then make it dissimilar. So this is in the expression below. So you put closer things together and different things far apart. And otherwise you do gradient descent in the both sides. So why this is such a big deal about this negative example? So conceptual, if you have to create negative example, you kind of need to say what is not an image. You say, well, I have a dog, and I somehow need to tell the network what is not a dog. But I don't know what is not a dog because I don't have any labels. And maybe it's not only the dog that I'm embedding, I'm also embedding the grass and the trees. Right? So conceptually somehow difficult to define what is not a dog. So the basic thing is that, well, I use all the other images. And so this could be computationally expensive, it is. So that's why you say, well, I will only use not every other image data set, but in the current batch of the data. So let's have, I have a batch of 4,000, and I said, well, my definition of not a dog is all other 3,999 images. Maybe I'm right, but maybe some of these are dogs. So actually, I cannot really be sure. I'm just hoping that I'm not making a mistake. So that's one. But you can say like an image is kind of easy, but in some domains it could be actually super difficult to decide what is not something. Like for example, reinforcement learning field that I work, for example, you need to embed trajectories of the agents that explore the room. What is not a trajectory? What is a very different trajectory that should be embedded in different space? It's not clear. What is not a sound? What is different sound? What is not a neural signal? What is a different neural signal? Can I use the different other signals? Maybe they're same. So that's kind of one of the things that why we're very happy that we have where we don't need to define the negatives because we potentially could be wrong. But another more practical thing is that it's a scalability. For noded object, and we see how on examples we need large batches because we cannot just have batches of 100 because 100 random images for not a dog are not a good definition of what a dog. So the largest batches work much better, and this is something that doesn't scale well. But what is even more important for one domain we applied is recently for graphs, it actually scales in quadratic in a sample size. So if you have a graph of nodes and you want to embed every single node, you need to decide what is different node. And so the things that works better with SymClear with a method called Grace, he said, well, I give embedding of the same node close together, and embedding of this node and every other node in the graph, I make loss so it goes away. So they're different away. Well, if there are n nodes, you have n squared, well, n times n minus 1, n squared different things. And this just doesn't fit in the memory. And so that's why you need to downsample, and you cannot use as much data as you would like to. And so by removing this thing, we're able to scale graph representation learning to like a really large scale. And the other thing that I will describe empirically, that once you don't have these negative examples, the network doesn't overfeed on your augmentation. Because simply what it's trying to do is trying to I just want to be invariant to all these augmentations. And when it is invariant, then it doesn't, doesn't learn anymore. So you need to have a lot of different diverse augmentation because you want to be diverse from every specific thing. All right. So it's 40. I should ask questions, but I should ask for a question. But if there are any questions, that's a good time. If not, I'll talk about next topic that I have. All right. So let me tell you about the result. So since this is a unsupervised learning, it's very difficult to evaluate because we don't have labels, right? So you cannot just run it. So the practitioners agreed in several ways of evaluation, and one of them that I'll present is this linear evaluation protocol on ImageNet. So what do? You take the training of your network, and you learn it after the convergence. So typically ResNet 50, and you use it and you train with all the self-supervised method that you want to evaluate. Then in second step, we freeze the encoder, so the weights will never move, will no longer move. But we add one linear classifier on top of that, and we train just the weight of the linear classifier. If encoder is good, then we get better results here. If encoder is really bad, well, the linear classifier doesn't have much capacity to learn much more things, right? So that's the purpose. But for this linear classification, we already use labels. Use a set of labels that are given to us, right? So there is no longer self-supervised learning. So you can even think of that this evaluation protocol is just a fully supervised learning, because here you did some kind of pre-training, and then you did some kind of not fine-tuning, but you added one more layer on top of it. And look at the example. This is a basic metric that of course there are people that don't like it, but this is the basic metric that people look at about the methods, about the self-supervised method. All right. So the reference point, we now show the accuracy of a supervised baseline, right? So this is kind of fake upper limit. Is that we don't train the network in a self-supervised way. We use all the labels and we train it, ResNet on ImageNet, full gradient descent until the convergence. So this is where the supervised the results are. The higher the better, and the X here indicates multiplicative factors in the channel of dimensions. So we have ResNet 2x, and LaTeX 4 times multiplier. So at the submission time, this was the state of the art compared to each other. So this is the simple method that uses contrastive learning. So pairs close together place further from each other. And Bile was successfully able to manage to almost close the gap between supervised learning and self-supervised method. And also unperformed simpler, which was the state of the art at the time. It's not impossible that self-supervised learning could actually go over supervised learning. It doesn't mean that it's a hard threshold. It could be that it's neural network could be able to better be trained in the completely pre-training because they don't suffer from bias from labels, and then they're better at it. But oftentimes, this is, we cannot get much better with no supervision than with supervision. All right. So these are some other benchmarks because, for convince people to use a method, this top one accuracy is enough. It's not enough. A lot of people have their own downstream tabs, so if you propose self-supervised method, you usually need to do a lot of benchmark, a lot of different tests. So this is, for example, segmentation. This is mean intersection over union, and so I will not go into details in that estimation. But we can say we did well on this whole other benchmark, which is not this top one accuracy. And it's important to know because the hope is that embeddings that are coming from the training of the ResNet are universal enough to be used for any task possible. So, in a summary, that Bio outperforms this other supervised learning method on these following benchmarks. You can also if there's other evaluation in the paper, then you start the network with the learning weight, and then you fine-tune them on some other data. So this is something how you can take advantage of our work, because we published both the code, but also the weight of the network. You can take the network, and then if you have your own data, which is not ImageNet, you can start the network with the weights that we provide on GitHub, and then fine-tune them. That should take much less time and much less computing power for the data set you have. You are interested in, and we saw how it works in about 20 data sets that are in the paper. Right. So the big summary, the Bio is less sensitive to the choice of image transformation, and it's more robust to the bad size. But for that, I have specific examples. So here, this is the best performance of bio and C-clear. Let's say we put them at 0, and then we try to remove some transformation. So if we remove, if you have less transformation, the final performance decreases. That's normal. But what is important to notice that for bio it decreases much less. This is due to the intuition I gave you because simplest tries to be as distinctive for a transformation it has, but one is for that reason it needs to have a big set of transformation, and it's very sensitive that it says it's diverse. And if you for example remove grayscale tolerant, you get performance which is 25% to point less. But our method is much less sensitive to that. So that means that you need to spend, let's say, less human time in designing a good transformation, and that's good news for a practitioner. Another good news that is that, and this is very much expected, and this is very on point. The bio is much less ready to do batch size, right? We do almost as well with the large batch sizes of 4,000 as in the batch sizes of 256, while performance of C-clear drops. And this is obvious, right? C-clear, when he takes a batch of data to training, he uses for each point in the batch, he tries to find transformation of that point and be closer to that, but all of the other, let's say, 4,000 points to be different from that point. Well, and as example I was giving, if these 399 or even more examples are not the dog, this is good. But if you have only 128, then it's not significant enough to define what is not the dog, and that's why the performance suffers. Of course, we suffer from the batch size too, but in a much less way. All right. So I have 12 minutes. 2 minutes. I have 2 minutes. So then maybe I can ask if there are any questions. Yes.
So maybe the answer will be in this section. So the question is, can we replace this exponential moving average by just adding some noise to the weights of our network, freeze network?
When you're doing the training?
Yes.
You could. So the hope is that the hope for exponential moving average is that it's averaging multiple things, and that helps the stability of the labels. So what are the neural networks good at is to
Yes, but if you're just adding noise, then you have your latest point, and you
have latest point, yes,
and so it doesn't matter if you average to this point or it's if you're on the same distance. That doesn't matter.
Yes.
How you got there.
So I still object to this, because if you have the last point and you add the noise, and this last point is moving, then if you add the noise, well, that says white noise, then the whole thing is moving, right? So it's still less stable. If you average things, by Chernoff-Hofting bound, you see, like if you average last numbers, then the average concentrates exponentially fast to the point. Maybe you decrease it by some weight, but the average is something that is much more stable than each point. And so it is more about averaging multiple points that creates a stable prediction. Of course, if you take something old, it averages something which is very bad. So that's why it will exponentially decrease. But if you only add noise, then it will not be stable. But maybe I can have besides this, we tried. Of course, we tried to. I think at some point we tried to remove the. I think the one of the answer to the question will be if you don't have the target network, if you remove the things that are stale, and I think we didn't do as well. I don't know if this is the example that we tried to remove the predictor. We tried to add also contrastive pairs. So we tried all these ablation studies, and some of them, maybe this one, yes, okay, this is exactly. So if you remove the target network, so it barely learns. So it learns something, but it's it's very small. So if you don't believe my theoretical explanation, we try that, and this is what it is. Yes.
I think my question is somewhat related. So in the beginning, you have two random networks, and you said that, if I understood you correctly, so even if you do that, even if you don't do the weight propagation from top to down, even then there is some learning. And if I understand correctly, that is crucial. If that doesn't happen, then so you need some signal in the beginning, right?
Yes.
So what's the intuition behind it? So what is happening in the neural network that even in this random initial state there is something?
Yes. So what is happening in down? Like even if it's different to have random labels and have labels from network with random weights, because even the network with random weights it encoded some biases, and it projects the data in the space, which which similar feature will be closer to each other. Maybe not as good as you would like to be, but much better if you pick a label randomly, which has no sense. And maybe this also could provide some information, because for our understanding, we try to see if we can completely remove the target network and not use the network. And we find out that if we make predictor optimal, so this is not possible because you cannot have an optimal predictor, but making predictor optimal you can replace by doing the learning rate, which is just much faster. So you have you have learning rate for the top part, but for the predictor, for this multi-level predictor, you take it, for example, 10 times faster, 25 faster. And if you take it 25 faster, then you can completely remove the bottom network, and so you never have even this random label from beginning. You have just one line, and you're training from the from the targets that you have from the same line. And in that case, you kind of have this difference because one part of the network is learning faster, and you don't get the best possible accuracy. 374%. You get something almost as close. So the target network is not really important. This is some kind of proxy for the signal to give us something to train on, but we can replace it with other things. So which hints us that there's probably some underlying principle that we don't understand, I don't understand, that you can do this principle by having the fast predictor or by having the target network. But there's multiple ways, so it's not that crucial that it's target network, it's like that. It's not crucial, but there is something, and we still need to find out what exactly is that the signal that is used, but it's not there. At least good practical point of view is that we have at least two ways to get to that.
So my question relates to the kind of similar question to how you initialize. So you mentioned in the beginning you have this 12 or like n random transformations. So do you include the seed of those, the random into the hyperparameters as well?
No, seed is not a hyperparameter.
But do you play with the seed? Like, does that add any kind of bias or anything?
I mean, we try. I don't remember how we average over multiple seeds. Not that many, because it takes a lot of time. But no, it's not important that you have one specific seed and you try to other specific thing. We actually, the stuff that was the most exciting to us was that a lot of self-supervised learning methods with different kind of structure sometimes collapse and sometimes don't. Right? For example, if you have a right seed, you can get the collapse, and if you have a wrong seed, so you try multiple seeds, and sometimes you collapse to the uniform presentation, and then it's useless, right? So what was striking for us, no matter what seed you use, in all the experiments we did for a year on this, and we did many experiments in parallel, we never collapse. The net collapse never happened. So there is power in this. We may not always get 74%, but it always learn. Except with these ablation studies, what we try to see what is crucial, right? So if we, for example, remove, if we remove predictor, we get 3% less, right? If we, or if we, for example, if you remove predictor, we collapse. If you remove target, we barely learn. If we add explicit negative examples, because that could be helpful, right? We get little improvement, but it's not significant enough to to use it all the time.
Thank you.
Thank you. I'd like to ask one question. You mentioned that when you remove the predictor, network collapses, the learning collapses. There's another paper that came after yours, the Dino paper, distribution with no labels. So they pretty much, instead of removing the predictor from top, they added predictor in the lower lower row, and they claim to have great results. Have you tried actually the same architecture that you have with Predictor?
No, we didn't. But I think if we just start a predictor on the bottom, we get the symmetric thing, so we would get the same thing. So for us, it was not that. It doesn't really matter if it's on the top or the bottom. There's one thing that I didn't have a talk about. We actually in some other methods. So this is a file for video paper that just got accepted to ICCV in a couple months. So then we actually have a predictor both on the top or the bottom. But the difference here that it has different modalities. So here we have a video of a narrow view, or this little part of the jump, and one a broad view. So people trying to jump and then jumping. And so this is like kind of, you can think of this as one transformation, selecting super small subset of the video, and this is another transformation selecting, let's say, 10 second views of the video. And here we try to put predictor on the both sides because there are different modalities. So we predict one broad view from the narrow and narrow from the broad. And for each of them, you have specific predictor. So I think when we have different modalities, that's actually helpful to have different predictors because they have kept kind of different data. If everything is just images from ImageNet, that's probably not that important. But I think adding predictor will not hurt it, but like removing it completely would hurt.
Thank you. So we'll take one last question before moving to the next talk, please.
A bit different question, but what do you think about distillation and self-distillation, and are there any unifying theory for this?
There is one paper that I know from, I forgot the name, but I can find it. I think it was also Peter Bartlett was one of the authors. It found that the distillation it can actually serves as kind of regularization. So there is some theory that the distillation has some kind of learning generation capabilities. So that's the only work that I know that could address. I'll send you the paper. It's from last year. There it is.
Thanks a lot, Michal. Let's thank Michal for a very interesting talk.